Hi everyone, this is Mr. Trong. I am back again with another tutorial session on another topic in IB chemistry. And so if you're watching this on Twitch live or watching on YouTube, um, previously recorded, thank you for coming to watch. Make sure you hit the like button and subscribe, and so you can get notifications for when the next videos come up. Today's topic is energetics or enthalpy, which is topic 5 SL for IB chemistry students. So whether you're reviewing for the IB exam or you're learning this for the first time in your first year of IB chemistry, welcome. And we're going to get started. I don't know how long it's going to go for. We're just going to try to cover as much as we can. I'm going to try to do it in the order of what the IB has these concepts in. So that's what I'm gonna work for. So let's go and get started. Okay. So the main focus here is enthalpy and a couple of concepts we want to do. Okay. Heat is a form of energy, and if you really look at it, a lot of the things about energy chemistry, there's thermal energy, there's chemical energy, there's electrical energy. So this is just one of the sources of energy that they want to kind of establish. And this is what all topic 5 is really about, heat. And so just a reminder, temperature reflects the average kinetic energy of the particles. So if the temperature goes up, the average kinetic energy of the particles also increases. Okay, we'll probably talk about that later on when we talk about Maxwell-Boltzmann curves, things like that. But so, and another note, conservation of energy. Okay, really important concept where energy is not created nor destroyed. So you can make assumptions about every reaction that the energy transferred has to be equivalent with depending, no matter which side of the process you're witnessing it from, the system or the surroundings. And so the amount of energy being transferred is always equivalent. Okay. And so the main focus of this is enthalpy. Okay. And which is symbolized by H. And essentially, enthalpy is the heat content of a system. Now, the heat content in itself is not really useful, but when we look at the change in enthalpy, we look at delta H, which is the change in heat content of a reaction from reactants to products. So what we're going to focus on in this topic is talking about, in a lot of different ways, how to calculate the change in enthalpy. There are a lot of different methods, and they're all using slightly different data, so it's important that you know which one's which, because you're going to be referencing different data that's provided to you in a data booklet, or you're going to be doing certain different setups for that. And we'll kind of go all through all that today as best as we can. If we run over 2 hours, I'm probably going to have to stop and continue later on, but we'll see kind of how this goes. And so another term you want to be familiar with is the standard enthalpy of reaction. Okay, and so the standard enthalpy of reaction is the change in heat content of a reaction for 1 mole at standard conditions. And is notated by a delta H with the degree. Okay, And that degree symbol, we usually say not to represent that, but that means standard conditions, okay? And for thermo, our standard conditions are 298 Kelvin and 100 kPa, which is slightly different for those that have studied the SAT2 or even on AP chemistry. It's a little bit different. AP chemistry uses 1 atmosphere. We use 100 kPa based on the IUPAC standards. Don't forget, if you're watching on Twitch, please feel free to type anything in the chat, questions. I've got almost only a 5-second delay, so if you type it in, I should be able to catch it pretty quickly and kind of stop myself and answer any questions that y'all have. Okay. But so we really kind of want to define a few terms here, other than these terms, obviously, the ones that we've just talked about, that will help me kind of explain things kind of throughout this topic. And so for our purpose, the system okay, is the reaction taking place. Okay, that's the only thing that's included in the system. The surroundings is essentially everything else. That's the air, even the water that the reaction is taking place in, if it's a solution reaction, all of that is the surroundings. And when you measure the temperature, that's what you're measuring of, the temperature of the surroundings. Your thermometer is part of the surroundings. So when your thermometer increases in temperature, that's because it's absorbing heat from the system that's being released. And so you really want to focus on the concept that the surroundings is where you're measuring the temperature always. You can never measure the temperature of the system. You can only measure the temperature of the surroundings. Well, let me be careful about that. When you're in a solution, you can't measure the temperature of the system. I guess one could argue that if you have like a metal block and you put a thermometer on there, that could theoretically measure the temperature system if you're measuring it, the metal block. But for our purposes here, we're not going to really kind of be considering that. Okay. And so we established two things, two types of descriptions for the transfer of heat. Okay. There is exothermic, where the system loses heat to the surroundings. Okay. And we have endothermic, where the system absorbs heat from the surroundings. Okay, so these terms we're going to use with respect to heat and enthalpy itself when we're trying to describe a reaction. So is a process exothermic or endothermic based on the value of delta H or even Q, which is also known as heat. Okay. And so an exothermic reaction will have a negative delta H of the system, because we always talk about it in terms of system right now. The endothermic will have a positive delta H, okay? So whenever you take the value of delta H out of the reaction and you give it context, you have to say whether it's negative or positive so that the person knows, okay, this value alone tells you whether it's exothermic or endothermic. If it's written in the reaction, it's obvious. If you have a reaction that looks like A plus B yields C plus heat, you can see that the heat is being, on the product side, it's being produced, so therefore the reaction's losing that heat. If you see A plus heat yields D, well, the heat's on the left. So on the reactant side, so you know the reactants must be using that heat to produce the product in the reaction. And so in the reaction, you always have a context because the location around the arrow, with respect to the arrow, tells you whether it's endothermic or exothermic. But when that value is taken out of the equation, it has to have context. And so you have to put a negative sign if you're losing it, or a positive when you're absorbing it, so that someone knows just by looking at the value, okay, where does it belong in the reaction? So that's a really important key. So when you look at your reference tables and things like that, you'll notice that the delta H's are negative or positive because they're not giving you a reaction, they're just giving the value, so you have to have context to that. So really pay attention to that. Okay. So the first way to measure the enthalpy of a reaction is calorimetry. Okay. I'm going to number these so you can kind of know. So the first way to measure enthalpy is using calorimetry. Essentially, what you're using is using specific heat of a substance to determine how much heat is being transferred. Okay, so specific heat or specific heat capacity, which we'll define in a second, is unique to every substance, and it is a given. It is a constant that you are provided with, or you may have to calculate using experimental data, but it's something that we can assume. And so when you look at specific heat capacity, it's labeled C, okay, which is the energy required to raise 1 gram of substance 1 degree Celsius. Okay, so how much energy do you have to put in for each gram of substance you have to raise the temperature of it 1 degree? And so for water, that's 4.18 joules per grams degree Celsius. So if you have 1 gram of water, to raise it 1 degree Celsius takes 4.18 joules of energy. Okay. Very funny to Bill. So that's actually a really large number, to be honest with you. Most metals and things like that conduct heat very well have specific heat capacities of like less than 1 or a little bit more than 1. And so this, as a side note, is really important property of water. It's really high specific heat capacity because it allows your body, which is like 75-80% water. I guess really if you break it down, it's really 90-something%. But just of water itself, it maintains a lot of heat. So when your body generates that heat, it's not lost to the surroundings a lot. It helps you regulate your temperature. The earth is mostly water, and that water is able to absorb a lot of heat and resist the temperature change that may be occurring as climate changes. And so really important that water has that kind of unique aspect that's really high specific heat capacity. Okay. Don't mix this up with heat capacity. Okay. Heat capacity, which doesn't really have a symbol, is the energy required to raise a known sample 1 degree Celsius. So whereas specific heat capacity is independent of how much you have, like if you have 10 grams or 100 grams, the specific heat capacity per 1 gram is always the same. Heat capacity is usually a value that you calculate for a cup that you're going to be using a lot of times, or a metal bar that you're going to be using a lot of time. And so this unit is joules per degree Celsius. And so what it's done, it's already factored in mass. It's already taken into account the mass of the system that is measuring, so you don't have to worry about it. So really pay attention to your units here, as you should always in chemistry, because that helps dictate what you need to know. In specific capacity, if you have grams to -1 degrees Celsius, -1, to figure out joules, you need to have a mass, and you have to have a temperature change. But in heat capacity, you don't need a mass, because the mass is already built into the value here. Now, this is where, and one of the equations provided in your data booklet, we get started with. And so that is Q is equal to MC delta T. Okay, and so to break down these values, or these letters, Q is heat. It's a heat of that individual reaction, that specific reaction that you're doing, not a general per molar heat, which we'll talk about later, like delta H is. Q is specific for each reaction that you're doing. Okay, M is the mass of this substance. C is a specific heat capacity. And delta T is a change in temperature. Okay. Now, what you need to make sure about is that these three values all describe the same substance. So if you're measuring the temperature of something and you're using specific heat capacity of something, then your mass should also be of that something. The biggest mistake students make is they look at a formula and say, oh, I need a mass. Let me find a mass in the problem. Whichever one's in grams, I'm going to use it. Well, the IB knows that. The IB knows that if you are memorizing just a mechanic to do something, that all they have to do is tweak the question so that that person doesn't get the right answer. And the person that understands what's happening gets the question right. It's a very thin line between tricking you and making a challenging question that only certain students deserve to get. And so be wary of that. Not sponsored by Diet Coke yet. Okay. So, because what they'll do is, well, let's talk about this. So Q is the heat of that substance, of that same mass, specific heat capacity, and change in temperature. And so if you want to figure out something, like if you have, let's say you have, 100 grams of water that is heated from 20 degrees Celsius to 40 degrees Celsius. Calculate the heat required. Okay. Thanks for the extra support, the bits, El Presidente. I know you don't take chemistry, but I appreciate the support on the stream. Okay. Oh, I need my calculator. 1 second. To be honest with you, I think this enthalpy topic, may actually be useful for the physics kids, because you do talk about this heat transfer and stuff like that. Maybe not using like enthalpy of formations, enthalpy of combustions, and stuff like that. But the calorimetry is a very common thing that's in physics as well. So calculating the heat required. Okay, this one is a fairly straightforward one. The Q of the water will equal the mass of the water times the specific heat of water times the change in temperature, which is final minus initial, which is 20 degrees Celsius. Okay, and so when you type that in, you get Q of the water is equal to 8,360 joules. Notice, again, I write my units out on every single number that I use, because I think it's really important, because it kind of makes sure that you are following the right pattern and that you can catch mistakes, especially when questions ask you to have the value in kilojoules or joules. You have to really pay attention to what your equation is actually trying to calculate. And that's one way they can trick you. You know, they'll give you the unit that you don't usually get the answer in as the requirement, so that way if a student isn't writing their units and they don't know what the value at the end of their question means, then they will get that answer wrong, and that'll be another mark off. And so that's another way you separate students. But so what they'll do is they'll say 5.0 grams of NaOH are dissolved in 400 centimeters cubed of water. The temperature increased from 24.6 degrees Celsius to 38.2 degrees Celsius. Okay, A. Determine the heat of the reaction, which is Q of the reaction, RxN for short. Okay. Now, okay, this is something that we also need to talk about, because Q of the reaction is not Q of the water. The water is the surroundings. So you'll have to keep that in mind when you actually get to that point. Okay. So the mistake that students make is they go Q is equal to MC delta T, and they say, okay, I know C is 4.18 joules per grams degrees Celsius. That's easy. Temperature change, 38.2 minus 24.6 is 13.6 degrees Celsius. And then I need a mass. And so then I use 5.0 grams. And that's where the mistake comes. And that's where the IB takes advantage of people that have just memorized a process and don't think about what the values actually mean, because they only see one mass. That must be the mass that you use for Q. But it's not, because this is of water. This is of water. So why would you use the mass of NaOH to complement the C and delta T of water? And so that's where students make a mistake. And so this should not be 5, but it actually should be 400 grams of water, because 1 centimeter cubed of water is equal to 1 gram. And that's only true for water. So make sure that you are familiar with that here. Okay. So again, I label this as Q of the water so I don't forget. And so this would be 400 times 4.18 times 13.6. And that is 22,739.2. If you're really going to sig figs, then it's 22,700 joules, or 22.7 kilojoules in that reaction. Okay. But that's not the reaction. The reaction is what is releasing that energy to the water. So if the energy absorbed 22,700 joules, then Q of the reaction is the opposite, which is negative 22.7 kilojoules. Okay. So, okay. So I know where this question is coming from. Some teachers teach Q of the reaction as negative M C delta T. And that's why I don't like putting that negative in there, because I think it's confusing. I wait to the end and do this concept. The negative sign, because the reaction and the water are opposite signs. So it appears to be a negative mass, but it's not really a negative mass. It's just that the teacher has taken the negative sign and put it into the equation so that you can skip a step. But I personally don't know the reason for that. And so I like to wait to the end, calculate my Q, and go, okay, if this is Q of the water, then Q of the reaction is negative. So you don't really have a negative mass. It's just that the teacher, to substitute Q of the water for Q of the reaction in one equation, has now put that negative sign in front of MC delta T. So that's just kind of a little mix up there. But technically what they're saying is true, but make sure you know why that negative is there. That negative is there to counteract the Q water equals Q of the negative reaction right here. Hopefully that explains what you're confused with. So that was the question. So the question is, why is that in some cases you use a negative mass and in others you don't? So you're not ever using negative mass, okay? You're putting a negative just to take care of that negative that's in here. Okay. Hopefully that clears it up for you. on that part. Okay. Feel free to speak up if it still wants some more clarification. Let me know. I'm going to go to the next part here, and so the second part here is where you actually get into enthalpy. And so enthalpy. So here you could determine the enthalpy, which is the delta H, change in H of the reaction. Now, delta H is per mole. So in usually kilojoules per mole. They'll tell you the unit usually for that. And so here you want the Q of the reaction. So delta H of the reaction, again, is equal to Q of the reaction over moles of the reaction. And so here we're going to use our negative 22.7 kilojoules. Okay. And we're going to divide it by the moles of reaction. And so the moles of reaction is not the water anymore. It is of the sodium hydroxide. The sodium hydroxide is what's releasing that heat. And so here you're going to want to convert that. And so whether you do it as, oh wait, I think I said 5 grams, didn't I? I said 5 grams, yeah, of NaOH. Whether you do it as a factor label, where it's 40.0 grams of NaOH per 1 mole, or if you do it as a proportion, 40 grams of NaOH over 1 mole, and then X moles. Either way, you get 0.125 moles. So then, therefore, you plug in 0.125 moles here, and then you're going to end up getting, let's see, negative 22.7 divided by 0.125, negative 181.6 kilojoules. Okay. So the reaction itself is exothermic, which already makes sense because the temperature of the water went up. So that tells you the reaction is releasing heat to the water. So that number agrees with the concept. And you'll find that in a lot of these lessons, I always try to focus on whether your number makes sense. Because if you can tell whether your number makes sense, that means you actually understand what's going on. Like, you understand that, hey, the temperature of the water went up, so that means the reaction must be exothermic. So if I don't get a negative delta H at the end, I did something wrong. That's the conceptual stuff that the IB is going to challenge you on and test you on. And so that's the real thing. Like, this, does the number make sense? Well, if temperature goes up, then the reaction should be exothermic, so therefore delta H of the reaction should be negative. So that's the key point here. Okay. Okay. Let's see. Okay. Now, when you're actually doing this lab with a calorimeter, you are going to have sources of error. You're not going to have a perfect lab. There's no such thing as a perfect lab. You try to minimize that error, but in this, there are things that you want to kind of focus on with error. The number one starred source of error in every calorimetry lab is loss of heat to the surroundings. You are always going to have heat being transferred to the air, being transferred to the calorimeter cup, whatever it is, there's going to be heat loss to surroundings. Not all of it transfers into the water, so you can't anticipate that. You can always minimize it. You can try to calculate how much is being lost to those different areas if you want to be really precise, but usually in IB, they're not going to expect you to do that. Okay? Now, the other thing is, like I said before, the calorimeter can absorb heat as well. And so factoring that in is really important when you're doing more precise labs. You're going to want to find the heat capacity of the calorimeter. So what you'll do usually is you'll take some hot water and cold water, put them together in the cup, and then see what the final temperature of that water is. And then you can measure how much heat the water actually transferred to the cup itself, and you can calculate the heat capacity of the cup. But I don't think you're going to have to actually do that for IB chemistry, but that's just kind of a concept. Okay. 3, this one's kind of nitpicky, but it is something that you use in your calculations. And so you usually assume that solution essentially equals water, whether it's in density. That's why you can assume that 1 centimeter cubed is equal to 1 gram of water, and also specific heat capacity, which is 4.18 joules per grams degrees Celsius. Now, again, you are making some assumptions because anytime there's something in the water, that affects the specific heat capacity, that affects density. But we're assuming that for our sake, to prove our calculations and to simplify things, that those things are equal. Usually the IB question will say that as well when you're solving it. But you can safely usually make those assumptions because the molarity usually is so low that it's 99.9% water, so it's not that big of a deal. Okay. Questions? I'm going to give about 20 seconds in chat to see. The specific capacity is in the data book. Yes, Petros. If you look here, I'm going to switch over really quickly. I should have had this up, but it's okay. If you look here, there is a set of values that you're given, and the specific heat capacity of water is provided right there in the middle there, 4.18 kilojoules per kilogram or 4.18 joules per gram. Just really depends on what mass you're dealing with. They're both equivalent because a kilojoule per kilogram is the same ratio as joules to grams. You also have the conversion of volume. 1 decimeter cubed is equal to 1,000 centimeters cubed. So keep that in mind that that's given to you there as well. So really important. And also, you are given, sorry, apologize, this is my Get to Know Your Data Packet lecture that I used last year. And so there's a lot of notes on the data packet, but it's okay. One day on stream, we'll do one of these to get to know your data packets and talk about all these different equations that you should know. But 5.1, which is the topic that we're talking about now, Q equals MC delta T is there. So you don't need to memorize that equation, but it's still one I would know because technically on the multiple choice, they could ask you about that equation and you don't have the data booklet then. So I've actually seen a question on the multiple choice before that literally asked, what is the specific heat capacity of water? So although it's in your data booklet, I would keep it in the back of your mind just in case they ask a dumb question like that, because that should be a free point. If you pay attention to all the units on the answer choices, there's only one right answer. So just keep that in mind. Okay. Okay. Any other questions about this before we move on? This is all of section 5.1. I'm going to try to tag certain times in here and try to keep track of where we're at. So I think this is about 37 minutes. I think I'm going to make a mark here because I'm going to try to label these times in the YouTube video so that when you watch it, you can kind of skip around and don't have to watch the whole thing and wait for me to go through every explanation. But so that's a tag for YouTube for later on. Okay. Let's see. Okay. Moving on. Actually, yeah, we'll move on. There is one more thing, definitions, but we'll save that for the next part. I don't think this is one of the shorter units. I think this is a little bit one of the longer units. Just because there's so much to kind of go over example-wise and problem-wise. It's a very math-heavy unit. Even though it's not really hard math, it is math that's very particular and very kind of specific. And so this is kind of medium to a little bit longer of the units. Okay. So the second idea, and this is 5.2. Okay. Which is Hess's law. Okay. Now, Hess's law depends on a couple of concepts. Okay. It depends on the fact that enthalpy is a state function. Meaning that all that matters is the initial and final points. That's all that matters. So state is only initial and final matter. Process is not important. So the pathway, I guess I should say pathway, if I'm really being specific with this, pathway is not important. So the best analogy I can think of is like in physics. If you're in physics, you know distance is different than displacement, okay? You can go from point A to point B in a lot of different ways, and you could travel a lot of different distances, but the displacement is just the measurement between these 2 points in the shortest possible distance. That's the displacement. Enthalpy is that way too. You can go through a bunch of different reactions as long as your reactants are here, your products are here. That's all that matters. It doesn't matter which pathway you go. And that's what Hess's law takes advantage of. So Hess's law says if reactions are additive, then delta H's are also additive. So what he said was that if you take reactions and you add them together and you get this reaction that you want, then the delta H's of those manipulated reactions, once you manipulate them, will also equal the overall delta H of that reaction. Okay. So with Hess's law, you have to know how to manipulate delta H. Okay, and delta H manipulates different than K, which is the equilibrium constant, which we'll talk about in another unit. But so here, manipulate delta H. That means when you work with the reaction, if you do something in the reaction, you have to do it to delta H as well. So for example, if I have A yields B and my delta H is negative 60 kilojoules. What that means is if I reverse the reaction for my purposes, then the delta H is 60 kilojoules. Because what I've done is I've taken this and multiplied it by -1 by reversing the reaction. Okay. If I double the reaction, I'm also doubling the heat. So delta H is equal to -120 kilojoules. Because I did 2 times -60. If I have the reaction, then it's the same concept. It's -30 kilojoules. So whatever you do to the reaction, you must do to the delta H as well. Okay, and that's really kind of important for this concept because that's what you do to get all the reactions to add up to the overall reaction that you want. Okay. I think I have a practice one here that I want to use. Okay. Now, calculating delta H for the following reaction. Okay, let's say this is your overall reaction here. 2N2 plus 5O2 yields 2N2O5. And below, wait a minute. Does this problem not have all the reactions? I don't think it has the delta H for this last reaction. I just noticed that when I took out the... Okay, you know what? This is what we'll do. Okay? Ignore these values. Because you may have to do this without numbers. I know that sounds a little crazy, but you may have to do this reaction without numbers. And so, on the multiple choice, without a calculator, they will just assign delta H values to letters. And then just ask you to write the expression to represent the delta H of the overall reaction. Oh, wait. I'm looking at this example now. I think what they did... No, that's okay. Okay, so my rule of thumb here is to do this for Hess's law. I always start with this. Okay, my rule of thumb is find something in the reactions that you're using that's only in one of the reactions that's in the final reaction. Because if that's true, then that has to match the coefficient, the location in the overall reaction. And so if you notice here, N2 is only in this third reaction, okay? And so therefore, this N2 has to be matching this N2 right here. So therefore, I know that this has to be 2Z, because I have to multiply this whole reaction by 2. I wonder if this bottom reaction is just a constant. No. This is a really kind of bad example. I really kind of thought that this was going to be... Oh, I know what they did. They just... Okay. Sorry, I just realized what this was. I'll admit, I looked at this problem and I went too quickly. And so then that bottom one, I see what that is. That's what the arrow is pointing to. They're talking about how they reverse that reaction. Okay, so my apologies. I figured out what's going on. Okay. This N2O5 is also unique to one reaction. So it is unique to here. It is the only reaction has N2O5, and that's needed in the overall reaction. So you have to make those match. And the way you do that is you have to flip the reaction and double it. And so what you notice here is that you're going to flip the reaction and double it. So that is 4HNO3 yields 2N2O5 plus 2H2O, which then flips and doubles negative 2Y. Okay. Now I'm going to flip the second one as well, the last one as well, so that we can kind of see, or not flip it, double it so that you can see what's here now. HNO3 and then 2N2 plus 6O2 plus 2H2. Okay, and that is equal to 2Z. So what I find is useful for Hess's law is I rewrite the reactions once I've manipulated them, so I can start canceling things out. Usually the IB will give you 3 reactions, and each of them will have a unique thing, and you can just match them up and don't worry about things canceling out, because they will naturally if you make everything else work. Because they're not going to give you extraneous reactions. They're just going to give you the only reactions you need. They're not trying to trick you again. They just want to make sure you know how to manipulate. So when you put these 2 reactions together, you notice that the HNO2s cancel out. Okay? Now, you still have a lot of things that you need to cancel out. You need to get rid of these H2s, these H2Os, and one of these O2s. Okay? Because you have 5 O2s left. Okay? So you have to use the last reaction here to cancel them out. And the only way you cancel things out in Hess's law is if they're on the opposite side of each other. Sorry, I didn't realize where the webcam was. So you have to make the 2H2O in the reaction here cancel out the 2H2O here. So what you have to do is you have to flip this and double it. So this is negative 2x. So I'm going to flip that and double it. So now this becomes 2H2O yields 2H2 plus O2. Okay, and that is represented by negative 2x. Okay, so now the 2 H2Os cancel, these 2 H2s cancel, and one of the O2s cancel. So now we're left with 2N2, 5O2, and 2N2O5. So that's your overall reaction, so you know it's right. So then your resulting equation is negative 2y plus 2z minus 2x. And you can rearrange this whichever way you want. It doesn't really matter. But that's what the delta H of the reaction should equal. Okay? And that's what we consider Hess's law. So the first tip I say is find unique substances. Make them match the overall reaction. So any substance that's in one of the smaller reactions, that's only in that reaction and in the overall reaction, then that has to match. So it's kind of dictating what you have to do regardless. And so that's how you do this. And so you're just making things match and everything else will take care of itself. If there is a reaction you have to wait on, then that's where you kind of have to be careful about that. Okay. And so that's kind of explaining how to use Hess's law for this, for example. I'm not going to do too many examples through this tutorial because then it takes a really long time. But if you have questions and you're watching the YouTube video or you're watching on Twitch, and you want to request me do some more problems, we'll keep that as a separate video, one that I can just upload on YouTube. I may do it on stream, I may not. We'll see. But this one, I just want to do one example for each and then to kind of give y'all a revision of this. And so y'all can practice these questions later on. Okay. Now, Hess's law is applied to a lot of different enthalpies. And so you may be given all the reactions, like in this problem where you're given the 3 reactions, you have to add them all up. Or you may be given values. And those values may relate to, let's choose a different color. We'll do standard enthalpy of formation, which is delta H F naught. Okay, so this is a specific type of enthalpy that you can use to calculate delta H of the reaction using Hess's law, and I'll show you how that works, and then kind of an easy way to remember it. Okay, so standard enthalpy of formation is defined as the enthalpy change or the heat change when 1 mole of substance is formed from standard state elements at standard conditions. Okay. You might think that's redundant, but standard state and standard conditions aren't necessarily the same. Standard state is a solid, liquid, and gas. Standard conditions is, again, 298 Kelvin and 100 kPa. So it sounds a little redundant because you're saying standard twice, but they're being used in different ways. Okay, and so what you can do is, for example, let's say I have CH4, and that's a gas. And I want to write the enthalpy of formation reaction for that, which is something the IB might have you do on the multiple choice or the short answer. You have to come up with the standard state elements for that reaction. And so it is carbon solid plus H2 gas. Now, to balance it, you need 2 H2s. So then now it's balanced. Again, this has to be 1 when you're balancing it. So make sure you keep that in mind. This is one of the rare times that you can have fractional coefficients, and it's okay. Let's do another one. Let's say you had CO2 gas. Well, that's, again, carbon solid and O2 gas. Water as a liquid, H2 gas plus O2 gas. But because you can only have 1 mole of H2O, it ends up being 1/2 O2. So each of these are enthalpy of formation reactions with respect to each substance, CH4, CO2, and H2O. So notice elements on the left and all the substances you're producing are on the right. So how does this work with Hess's law? Well, let's say this is X, Y, and Z for our delta HFs. Now, let's pretend the reaction you're trying to get is this. Okay. If this is the reaction, you can use those 3 reactions that are given to you to figure out what the delta H of the reaction is based on Hess's law. Okay, so we find the unique things. Okay, notice unique CH4, unique unique CH4. Now, it's on the wrong side with the right coefficient, so you just flip it around. So then this becomes CH4 yields C solid plus 2H2 gas. So that is negative X. Okay. CO2 is also unique. It's on the right side, or correct side already. So therefore we leave it alone. So that it's the right coefficient. So it's C solid plus O2 gas yields CO2 gas, which is Y. Okay. Then water, H2O, it's on the correct side, but you need 2 of them. So you multiply the whole reaction by 2. So this becomes 2Z. I want to clear that up a little bit. Z. Okay. So now what you can say is essentially 2Z plus Y minus X. Okay. And what this turns out to be is these are the products of your overall reaction. These are the reactants of your overall reaction. So it turns out it's just products minus reactants using coefficients. Okay. And so what this does is it helps you simplify. You don't have to write these reactions every single time you have to use enthalpy of formation. You can remember that products minus reactants. Okay. I still think memorizing products minus reactants is kind of iffy because you're having to memorize a lot of things in chemistry. And my philosophy is minimize what you have to memorize. And so I think it's better just to think of what an enthalpy of formation reaction is. And if you think about what an enthalpy of formation reaction is, well, everything you want in an enthalpy of formation reaction is on the product side. So all those values are going to stay the same side. But the one reaction or two reactions that have things that are reactants in the overall reaction, you need to flip them. So it's products plus the negative reactants, which is products minus reactants. So I like think of it that way and think of it in terms of the enthalpy of formation. So you don't have to memorize two things because you have to memorize the enthalpy of formation definition already. So why would you do that and then do products minus reactants? All you have to do is write one enthalpy of formation of any substance. You go, okay, the substance I have is on the product side, but the overall reaction is on the reactant side. So I have to flip it. So therefore, it's products minus reactants. So I think that's really kind of handy way to think about this to save you one thing you have to memorize. Because again, if you memorize it and you get it backwards on the test, on the IB exam, you'll never know because that's all you did. You just memorized that one equation and it's a coin flip. It's either products minus reactants or reactants minus products based on the type of enthalpy. And so it's just not a great idea for that. And so just be careful about that and try to think about this and kind of apply it a little bit better. But so that is enthalpy of formation. So products minus reactants using coefficients, that's the best way to do that information, I think. Okay. You probably are wondering, why didn't I involve delta H of H2 or O2? Because those are elements. And so the key thing you want to focus on here is delta H of the formation of standard state elements is 0. So you can assume that for delta HF that it's always 0 for standard state elements because those elements are in every enthalpy of formation reaction. So therefore, they're already factored in without having its own delta H. They're already given a value based on the delta H's of the overall reaction. So don't worry about elements. They're always 0. So you won't use this. You won't do this way every single time. You'll be provided the data table, the data packet, and you can use that. And so I'll pull it up on Dropbox so it's not written on. But so let's see. Is it this one? Yeah. Okay. So you can notice here that there's a table of all these delta HFs. Okay. Next one. Okay. So see delta HF right in the middle, and they're negative or positive based on the reaction. They give you all the compounds, state of matter that's standard, and then delta H's of all these. And so in the bottom is where the water, the CO2, stuff like that is as well. So make sure you kind of pay attention to that and make sure that you are using these values that are provided to you. So you won't have to write those enthalpy of formation reactions out every time. You just do products minus reactants. Okay. Let's take a 3-minute break. I'm going to just take a really quick break. I know it's a lot of stuff to take in, so I'm going to let y'all kind of throw any questions into chat for the next like 2 or 3 minutes. I know I'm kind of moving quickly, and so sometimes you kind of are afraid to ask questions, but I'm going to give you about 2 to 3 minutes to throw any questions you have up in chat, and then as soon as I get back from break, I will try to address any of those questions about anything we've gone over so far. Actually, we're not too far from being done, so I think we're looking at probably about an hour and a half to hour 40-minute stream, because the last thing we really have to do is energy profiles and bond enthalpy, and a little bit of ozone as well, just kind of very general concept of that. That's more of topic 4, the reactions, but the concept of the ozone bond energy versus oxygen. So we will take a 2 to 3 minute break, let y'all step away, get a drink or something like that, use a bathroom. Type anything in chat that you have a question about that we've gone over so far, and then I will address that when we get back from break, and then we will move on to bond enthalpy and energy profiles. So, all right. Did I close the... Where's my music? Boom. All right, so I'm back now, and we will continue this. And so we will talk about bond enthalpy, which is the last section of this SL topic 5. And so we should be good after this, and then we will finish up on that. So I didn't see any questions in the chat, so I'm going to assume that we're okay. And we're going to get back to this lesson. And so we are at, let's see, because I ran the stream before. I think it's about, let's say, 1:08 for YouTube. And this is where we'll start 5.3. Okay, so this is 5.3, which is labeled bond enthalpies. Okay, now what you want to understand here is that every reaction breaks and forms bonds. Every reaction. It doesn't matter. Any chemical reaction that's happening, there's a bond, at least one bond being broken and one bond being formed. And so when you look at something like, I don't know, N2 plus 3H2 yields 2NH3. There are bonds being broken on this side so that the N's can separate from each other, the H's can separate each other, and then they can form on this side. And so this is the main concept of using bond enthalpies to calculate the overall reaction, because the sum of those two values of the bonds broken and bonds formed gives you your whole delta H value. And so this is where we want to establish what bond enthalpy really is. Okay, and so bond enthalpy is defined as energy needed to break 1 mole of a bond in a gaseous molecule. Okay, now an addendum to that is if you put the word average in front, okay, you have to add the fact that it is averaged over similar compounds. So like a C to C bond is in billions of different compounds. And so they take several compounds that have a C to C bond, they break them up, and then they average it. So like even if you have, like, let's say you have CF4, you can't break one bond at a time. You just have to give energy to break all the bonds. And so what you do is you break up the carbon and 4 fluorines. And so you break up all 4 bonds. Then you take that delta H of that reaction and then divide it by 4 to find the average bond enthalpy. Okay, so you break up all 4 C to F bonds and you divide it by 4 to figure out the average bond enthalpy of one bond that you're breaking. Okay, so really what this is saying is that if you had something like this and you made it into something like this, that's what that represents right here. When you divide by 4, that's what you're saying. If I broke only one bond, what would the approximate value of that energy be? Okay, so keep that in mind. Okay. Now, your bond enthalpy table has all positive values. Okay, that's because it is breaking the bond. Breaking the bond requires absorption of energy. So it is considered endothermic. Because the reason why atoms bond is because they have a lower energy state when they're bonded, sharing electrons, versus when they're apart. That's the only reason why things bond. And so to pull those atoms apart, you have to put in energy to separate them. It's like two magnets. If two magnets stuck together, if you want to separate them, you have to put in energy to pull them apart. That's what bond breaking is. It's endothermic. You have to put energy into the magnets so that you can hold them apart from each other without them coming back together. If you make bonds, you release those magnets and they come together, they make noise. They release energy that way. So keep that in mind when you're thinking about the signs of these values. But so, when you do a bond enthalpy problem, here's what I find is the best thing to do. I find the best thing to do is to draw out all your bonds, because there are way too many instances of students rushing through this problem, not counting their bonds correctly, and then they get it wrong. You got to understand that this, for an IB question, is 3 marks. 1 mark for the bond enthalpy of the reactants, 1 mark for the bond enthalpy of the products, and then 1 mark for the bond enthalpy of the enthalpy of the reaction. So if you get either the reactants or products wrong, you've lost 2 marks already, the final answer and the one that you got wrong. So it's important that you do 2 things. 1, write out each side and add them up so that you put the value on the paper. So at least you might get 1 mark if you get one of them wrong. Don't just try to do it all in one step and then not have the values, because I don't think the grader is going to go through and check to see if you wrote all the right values. So I would do all the bonds broken, all the bonds formed, and use those values, and then write out the product side, the reactant side, and then combine them together to make sure that you get maximum points. So for example, something like this. N2 plus 3H2 yields 2NH3. I write out all the bonds because students always just try to use the coefficients and then they get it wrong because some molecules have more than 1 bond. And then sometimes they forget what type of bond it is. N2 is actually a triple bond. So that matters. H2 is a single bond. And then NH3 is also single bonds. Okay? So when you look at this here, on the left, you have 1 N triple bond N, and then 3 H single bond H's. On the product side, you have 6 NH bonds. That's where kids mess up, because if they just got the coefficients, they would write 2 NH bonds. But there's 3 on each of them. So it's actually 6 total bonds here. So what we have to do is we have to look at the value for these bond enthalpies. And so looking at the chart here, actually, I'll show you it on here because I think it's really important you recognize these values. So this chart is written in a specific way. It's a cross table. And so what you do is you just pick the 2 elements that are bonded, 1 on each axis of the table, and then you cross them until they meet together, intersect, and that's the value for that. And so here you're looking up H to H bonds. So you go down from H across to where H meets at H, and that's 436. So for an H bond, it is 3 times 436. Okay, and an N triple bond end, triple bonds are down here, is 945. So that's 1 times 945. And you add those together. So 945 plus 3 times 436. And that is 2,253. Okay. So on the product side, you have 6 NH bonds. So you look it up here, and you say, well, NH is cross, which is 391. So this is 391 kilojoules per each bond. So 6 times 391 is 2,346. Okay. Now, the question is, where are you breaking bonds and where are you making bonds? Every time you break bonds is on the reactant side. So that part is always positive. Okay. When you make bonds, you release energy, and that's always on the product side. So that side becomes negative because you're releasing that energy as those bonds are being formed. That potential energy is being released because you don't need it anymore. And so what it ends up being is 2253 minus 2346. And that is negative 93 kilojoules for your reaction here. Okay. Some books will just say reactants minus products. That's fine too, but you don't do the negative number I did up here and then do subtract. You either subtract or you make it negative and then you add them. Okay, so make sure you think about that when you're trying to figure this out. So you either do reactants minus products or you do reactants plus the negative of the products, but just don't do both because then you're going to be on the wrong side for sure. Questions about that? Give about 10 seconds, 15 seconds for people to ask questions about what I did there. So reactants break bonds, products make bonds. That's the key idea. Okay, I don't see anything on here, so we will start moving on. Now, there is one more thing. I'm looking at the concepts here that you want to take into account, which is why are bond enthalpies less accurate than delta H Fs. Okay. The reason why are a couple things. Okay. They only work for gases. So if your overall reaction has anything other than gases, your bond enthalpy is going to be slightly off because that phase change is going to require a change in energy as well. So you have to make sure that you understand that your value is going to be a little bit off. Okay. Also, do not factor in IMFs because even in your gaseous stage, there's some energy required to break the force of attraction between the particles, which isn't factored into that. They're assuming all the energy is going into breaking the bonds, but that's not true because some of it has to go into breaking the IMFs as well. Okay, and so, and again, they are usually an average of similar compounds. Every compound with a C to C bond has a different bond enthalpy technically, but we assume that they're all similar enough that we can just use that average to solve it. So if you calculate something with delta HF and you calculate something with bond enthalpy, you're going to have slightly different answers. Maybe even hundreds of kilojoules different because of the states of matter of everything. So that's okay. Now, if you get the wrong sign for the two values, then you did something wrong. Like there's no way I can think of that your signs would be different for delta HF calculations and bond enthalpy calculations. Yeah. So let's add a couple more things in separate concepts to kind of clean things up and kind of wrap up this. And so, one, standard enthalpy of combustion. Which is delta H C naught. Okay. That is the energy change when 1 mole of substance undergoes combustion at standard conditions. Okay, so it looks like they've removed the enthalpy of combustion calculations, but you can just do Hess's law for that anyways. All they really want you to know here is what does the actual value that's given in your data packet represent chemically in a reaction. And so if you have the enthalpy of combustion of C2H6, the reaction for that equation is for that value is C2H6 plus O2 yields CO2 plus H2O, and to balance it, it's 3, 2, and that is 7 halves. It's okay to have fractions because this has to be 1, no matter what. So understand that the delta HC is just the enthalpy of combustion reaction. So reacting with O2 to form its products. And those values are also given to you in your data packet. Down here. Sorry, it's sideways, but these are enthalpy of combustions, okay? And so at standard temperature and pressure, 100 kPa and 298 Kelvin. And so you have all these substances with all their values. Notice all their combustions are exothermic, which we define combustions as exothermic, along with neutralization equations. Okay. Now, 2 more things. Okay. Let's see. This is maybe 124. Okay. Energy profiles. Okay. Energy profiles, reaction energy diagrams, they're kind of really one and the same, except they have additional things added on their graphs. But I'm going to kind of treat them the same way. And so an energy profile looks something like this. And there's 2 of them that you want to kind of observe. Okay. This might be more considered a reaction energy diagram if you're really being specific, because it has the Hill and the activation energy, but I think it's fine if you draw it this way for an energy profile. And so an energy profile shows your potential energy, and it shows your potential energy of the reactants and the potential energy of the products. And the difference in those is your delta H. Now, it's important that you recognize that delta H, again, is that difference between the reactants and the product. It doesn't matter how tall the hill is. It doesn't matter how wide the reaction is, because that's just progress. It's not time. The delta H is the difference between the products and the reactants. So in both of these reactions, the products are less than the reactants, which tells you that it is an exothermic reaction, because if the products have less energy than the reactants, then the reactants must have released energy along with making the products to get to that state of potential energy. And so you're releasing heat, and so all of that is under your delta H concern. Okay. The lower the energy state also means the more stable it is. And so because the products are lower here, we consider them more stable. In an endothermic reaction, the reactants would be more stable because they're at lower energy state than the products. Okay. We won't go into activation energy. That's for another topic. But the main things you want to focus on, the fact that there's reactants here, products here. In your book, the profiles may not even have the hill, because that's more with reaction energy diagrams. But all that matters now is the delta H. I didn't notice it was 2 exothermic reactions. That's my fault, because I wanted 1 of each, but that's okay. The last thing that we have to talk about here is ozone. So this is tying back into environmental chemistry and how ozone works in the atmosphere. And so the key thing here is that what you need to understand is this. Okay. The fact is that the ozone layer consists consists of O2 and O3, which is ozone, in equilibrium. Okay. Now, oxygen looks like this with the double bond. Ozone has resonance. So the double bond flips back and forth between these two. Now, what it turns out is, what ozone does is this, the bond energy, bond enthalpy, they're the same because it's about 1.5 bonds, 1.5 bonds versus 2 bonds. It turns out the benefit with ozone is that this bond enthalpy absorbs radiation from 280 nanometers to 315 nanometers. Okay, this is considered UVB, and this is the second most dangerous UV radiation that can be emitted by the sun into the earth. UVC is the most dangerous, but there's no way that stuff gets through the atmosphere, and so it's all kind of reflected off of the top of the atmosphere, and so you don't really have to worry about that. But UVB is just the right amount of energy so the wavelength is able to pass through a lot of the atmosphere, okay? And it's high enough energy that it can actually do damage to your skin over long exposures. And so that's why people that get sunburns that are in areas where the ozone layer is depleted, there's more of a risk of getting skin cancer because that UVB radiation is what really causes that damage, okay? And so that's the purpose of ozone. And so ozone's bond strength, because it's a little bit less than oxygen, absorbs right in the right frequency to be able to do that. And so they might actually ask you to calculate the wavelength absorbed by ozone. And so this is the last calculation we'll do for today, and then we'll call it a day. You can look up here and find the bond enthalpy of ozone. And notice, actually, I don't think they give it to you here. Oh, they don't give it to you here. So you'll have to figure it out yourself. I'm pretty sure that it is... oh, I need to make sure I look this up correctly because I want to make sure the value's right. Give me 1 second. Okay, so ozone has a bond enthalpy of 142.7 kilojoules per mole. That's strange. Because you would think it's slightly... Am I reading this wrong? Nope, it says... Enthalpy of formation is 142.7. Wait, no, that's enthalpy of formation. Hold on a second. That's not right. Because, like, that didn't make sense because it should be between an O single bond and an O double bond. And so, let's see. I'm trying to figure out. Okay, I believe it's 445. That makes more sense because if you think about it, it should be between the two values of single bond and double bond. So single bond is 144, and that's 498. That's still a little bit high. I gotta double check my values here because that seems a little high. But I don't know if I have a source. No, see, it's 360. Okay, hold on. sorry, my sources keep telling me different things, but 364 makes more sense because it's right in between a single bond and a double bond. So we're gonna go with 364. Okay, so that's per mole though, and it's asking you to calculate the wavelength absorbed by ozone, and that's per one atom. Okay, so the first thing that we're gonna have to do is make this into first joules per mole. And then we have to divide by 6.02 times 10 to the 23rd to figure out how many joules per bond. Because a mole is of 6.02 times 10 to the 23rd bonds. So, 364. We get 6.047 times 10 to the negative 19th joules per bond. And then we can apply, this is a little bit topic 2, but still something that you want to think about here. E equals H nu. So energy, 6.047 times 10 to the negative 19th joules is equal to Planck's constant, 6.63 times 10 to the negative 34th joules times seconds, times frequency. So we divide by Planck's constant, and we get a frequency of 9.12 times 10 to the 14th hertz. And then C is equal to lambda nu, so the speed of light is equal to lambda times 9.12 times 10 to the 14th seconds to negative 1. So then, and you get a wavelength of 3.29 times 10 to the negative 7 meters, which then, when you convert to nanometers, is 329 nanometers. It seems a little bit outside, but there is kind of a bit of a range there. And so I'm wondering if my bond enthalpy is a little bit off, but the idea is that it can absorb some of that frequency that's kind of relatively close in that range. And so that's just to kind of show you how to calculate what the photon that's required to break a bond is. So you would use the bond enthalpy, convert it to per bond, and then use the energy equation, the speed of light equation, to figure out the frequency. So they might ask you what frequency or what wavelength is required to break an ozone bond or any kind of bond using this calculation. But so, that's the main thing about here. So you really want to just know ozone's bond enthalpy is slightly lower than oxygen's, which is double bond, and therefore it absorbs the certain wavelength of light that's UVB from the sun. So it absorbs that, converts itself to oxygen, and then absorbs it, prevents it from getting through the atmosphere into our into the ground, toward the ground to for us to be exposed to it. And so that's the main kind of concept here with ozone. In topic 4, when we go over that, you'll talk about the free radical reactions that form oxygen and ozone and how they kind of work back and forth, and how chlorofluorocarbons and other fluorocarbons can affect that equilibrium. But so that is essentially topic 5. We went over endothermic, exothermic, we went over calorimetry, we went over Hess's law, we went over enthalpy of formation, we went over bond enthalpy, we went over enthalpy of combustion, we went over ozone, and we briefly went over energy profiles. And so that's it. Thank y'all for those of you that are watching on Twitch. Thank you for those of you that are watching later on YouTube. Make sure you hit a like on the YouTube video and hit subscribe, and that should set up the notifications so that you'll get the next YouTube video of my lessons on this. And so I'm going to stop recording right now. And so I am Mr. Trong, and class is dismissed.